I would like to welcome you all in the lecture series of power electronics. In this session, we are going to discuss single phase full wave converter. It is also known as controlled rectifier. In the previous session, we discussed about uncontrolled rectifier, but here we are using like a thyristor for making to control to prepare the controlled rectifier, to design controlled rectifier. So as you can observe, the control rectifier comprises of the following segments. First of all, you can observe the components which is used in single phase full wave converter. So we have four thyristor T1, T2, T3, T4, which is connected in the form of a bridge. Then we have the transformer, correct? So there is a primary winding and secondary winding. Here you can see the core. Next, we supply entire power to the load. It is actually highly inductive load. It is basically RLE load. Okay. So it represents motor, DC motor. So the ultimate goal is we need to convert the AC supply, AC power to DC power. So here the thing is you can control the output voltage. But in uncontrolled rectifier, we cannot control the output voltage. That is a peculiarity of single phase full converter, which is designed by using thyristors. Correct. Now we'll discuss about the operation. How does it work? The working is very simple. You should know what is the difference between positive half cycle, negative half cycle, and the current flow. Then your job will be completed. First of all, we discuss about positive half cycle. So during positive half cycle, what is going to happen? So during positive half cycle, we can say that T1 and T2 conducts. Also, the thyristor T1 and T2 conducts when omega t is equal to alpha. Let me discuss what is going to happen during positive half cycle. First of all, you have to mark like a positive, this is positive, and this is negative. That is called a positive half cycle. So in positive half cycle, current flow in this particular fashion. So thyristor will conduct because it gets forward biased. Thyristor T3 will not conduct. Why? Because it is in the reverse biased. Because positive comes to cathode means that become reverse biased. Then current flow in this fashion, it will directly move on to the load. Okay. Then coming back here, then it will come back to it will come back to where then negative. For example, it will come back here. Sorry, it will come back in this fashion. Then come to the negative end of the supply. So this you can strike. Okay, it will come back in this fashion. Then through T2, it will come back to negative end of the supply. Here you just tell me T1 and T2 will be conducted at the time of a positive half cycle. It will conduct T1 and T2 will conduct when omega t is equal to firing angle alpha. That is why it is called a controlled rectifier, where alpha is known as firing angle. Firing angle. Okay. Based on the firing angle, you can vary the output voltage by changing the firing angle. That is a peculiarity. Now, please refer the waveforms. So in this waveform, we can observe like how it is going to work very clearly. So the waveform shows that. So please check the waveforms. So we provided the input. Now during positive half cycle, T1 and T2 will be conducted. So the device will conduct when omega t is equal to alpha. Omega t is belong to x-axis. Okay. When omega t is alpha, it is going to conduct. And since we are using the inductive load, so we can see the like output. You can see the like output voltage in this fashion. You can see like in the inductive load, there is a like a phase shift between voltage and current. That is why there is a like what I can say one more waveform which is going to the negative direction. Ultimately, we can say during positive half cycle, T1 and T2 will conduct, and we can mark during positive half cycle, the operation will be in this particular area. Okay, this is the output voltage. Now we'll see during negative half cycle what is going to happen. So let me consider the circuit diagram once again. Now I'll mark the negative half cycle. So let us see how the current flow takes place so that you can understand the working very clearly. Here instead of positive, we'll mark negative, and here we'll mark positive. You already know that current flow will be always start from positive, then come back to negative. Now please check it up. T3. Now T3 will conduct. Okay. Then come back to the load. then current passes in this particular fashion. Now we can check it up. Then it comes back to T4, then approaches to the negative side. So this is the way how the direction of current flow. Okay, you can check it up. So start from positive, end to negative. Here the peculiarities, T3 and T4 is going to be conducted. T3, T4 conduct when omega t is equal to alpha plus pi, pi plus alpha. Let me show you in the waveform so that you can very clear the concept. You can clarify the like working in a proper fashion. So I'll take you to show you the waveforms. So please pay the attention. Here you can observe during if I talk about like a negative half cycle, T3 and T4 conducts when omega t is equal to pi plus alpha. Here pi plus alpha is the, yeah. So it will work in the uh, other quadrant, first, second, third, fourth quadrant, correct, no? Yeah. ASTC, then it's a fourth quadrant, of course. So T3 and T4 conducts in this particular region. You can see the current pulse, the current waveform will be in the form of like a square pulse only, because since we are using the inductive load, we will be getting like a current in a square pulse, correct? So these are the important waveforms concerning single phase full wave converter. It is also known as controlled rectifier, controlled rectifier. One more observation we can see, I have written the explanation very clearly. Positive half cycle, what is going to happen when the device will conduct, that also I have written very clearly. If I talk about like negative half cycle, so who and all the devices conduct during this particular time, T3 and T4 will conduct. Similarly, during negative half cycle, how about the operation with the help of waveforms? That also I have explained very clearly. Now, this device will applicable up to 15 kilowatts application. If the load rating is 15 kilowatts, up to 15 kilowatts, you can use single phase full wave converter to convert AC to DC with a controlled fashion. So using the thyristors, you can easily use it. Okay. So that is a peculiarity of this particular device. Now, we'll talk about like the analysis, the mathematical analysis. You can check the you can perform one more important thing, that the converter during positive half cycle T1 T2 conducts at omega t is equal to alpha. At this spot, the device will work as a rectifier mode, where so on the conversely during the negative half cycle it will act as a inverter mode, rectification mode and inverter mode. This point also you have to remember. Now we'll do the mathematical analysis. Simple mathematical analysis we'll perform. So we can calculate the output voltage, DC voltage, anyway, across the RLE load, across the RL load, across the RLE load, okay, across the RLE load, you will be getting the output voltage, right? VDC can be written as 2 by 2 pi alpha to pi plus alpha. I'll be considering only like a one half cycle, Vm sin omega t d omega t. By integrating, you can put the upper and lower limit accordingly. I'll be getting VDC is equal to 2 Vm by pi cos alpha. So the output voltage is directly depending on the firing angle. See, output voltage is directly depending on firing angle. So output voltage depending on firing angle. So I can, so that is why it is known as controlled rectifier. Similarly, maximum average output you can write like a VDM. Put alpha is equal to 0. If I put alpha is equal to 0, what is going to happen? Cos alpha become cos 0 become 1. So the answer is 2 Vm by pi. So call it as equation number 2. The first one you can call it as equation number 1. Now take the ratio of equation number 2 and 1. 1 and 2, 1 and 2. Take 1 by 2. Okay, 1 and 2. So what will happen is cos like 2 Vm by pi get cancelled in both the side. So normalized average output voltage is given by VDC by Vm, that is equal to cos alpha. Correct? This is one analysis. Next, we will compute the RMS value. Let us calculate the RMS value. So we are going to compute the RMS value. So please have a look on this. Yeah, the RMS voltage is given by Vrms 2 by 2 pi alpha to pi plus alpha Vm square sin square omega t d omega t. So sin square omega t you have to convert. Sin square omega t is equal to 1 minus cos 2 omega t divided by 2. Then you can easily integrate. Apply the same thing here. Okay, apply the same thing here. Then you can compute the integration. This is a formula for RMS value. Ultimately, you will be getting Vm by root 2, that is equal to supply voltage. So this is regarding the RMS output voltage. So make a note of this. In the numerical example, you can get the similar kind of questions. Now, there are three type of mode. Like one is continuous conduction mode, discontinuous conduction mode, and a boundary condition. In the continuous conduction mode, we always remember that inductor current never goes to zero. It will always greater than zero. During the continuous conduction mode, during the operation, we'll be writing applying the KVL. When we apply the KVL, you can see the circuit diagram. We can apply the KVL. Okay, so it become a closed loop, right? So we can apply the KVL. Then at that time, you have to consider voltage across resistor, voltage across inductor, then battery voltage, then supply voltage. Correct? Supply voltage, inductor voltage, resistor voltage, the battery voltage. It's a closed loop, right? It's a closed loop. So we consider apply the KVL. Let's apply the KVL. It's a closed loop, or we call it as a mesh. Then while applying the KVL, you'll be getting the equations in this fashion. See, this is voltage across inductor, voltage across a resistor. This is the battery voltage, that is back EMF. Then the supply voltage, Vs. So voltage, sum of voltage drop and EMF, that is equal to 0. Apply the same principle over here. Yeah. This is basically called ordinary differential equation. Now you can come, already studied in mathematics how to calculate the solution. By providing the solution, by calculating the solution, I'll be getting in this fashion. Here there is a parameter called A1. Okay. Now I can write the value of A1. Okay. You have to apply the ODE, ordinary differential equation, the concept. Then definitely you will be getting the value of A1. Yeah. So I get A1 equal to IL0 E by R minus root 2 Vs by Z into sine alpha minus theta e to the power R by L alpha by omega, where Z is known as impedance square root of R square plus L omega square, since it is a inductive load, RL circuit. From that you can calculate theta. Tan theta is equal to L omega by R. Therefore, theta is equal to tan inverse of L omega by R. Similarly, you can calculate the RMS value of like a thyristor. T1, T2, T3, we can say we have thyristor. The average value during positive, you can compute the average value using this particular formula. Ultimately, you can calculate the RMS output like square root of IR. So average value of thyristor current you can compute 1 by 2 pi alpha to pi plus alpha IL d omega t. During positive and half cycle, you have to consider. Therefore, the average value of thyristor, that is equal to IA plus IA, that is nothing but 2IA. That also you are going to get. Fine. So this is a concept regarding single phase full wave converter. It is basically a controlled rectifier. Remember that it's a controlled rectifier. We studied the circuit diagram. Then we understood the aspects of design based on the mathematical formula, which I already mentioned. Then we studied the waveforms, then quadrant operations. Then we studied about the different modes we discussed. Okay, rectification mode and inversion mode. Then output voltage is directly depending on the firing angle. That is why it is known as controlled rectifier. So that's all about like a single phase full wave converter. If you want, you can simulate the same thing in MATLAB Simulink. For the other session, I'm going to discuss about the simulation. Let me know if you have any questions related to this particular topic. Happy learning. Have a great day. You can focus more. It will be very easy only. Any confusion, you can put up in the comment box. I'm very happy to answer back. Thank you very much.